You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that had, has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoy the podcast, please listen, subscribe, like, and share it with friends. Thank you.
Hello, this is Richard Jacobs for the Future Tech and Future Tech Health podcast. I have Dr. Zoran Radish. He's a scientist that's exploring the use of Russian nerve agent using a tool from a company called Nanome that lets you in 3D look at molecules and explore them, turn them, perhaps let them interact with other molecules, and super interesting. So, Dr. Radish, thanks for coming. How are you doing?
Very good, thank you.
Yeah, tell me, why look into nerve gas? How did this whole project start?
Well, quite a few researchers around the world are looking into toxicity of nerve agents, warfare agents. Some of them are gases, some of them are more in a liquid state. In order to find good antidotes to treat people exposed to nerve gases. One has to mention that the same family of chemical compounds are also organophosphorus pesticides that are used in every day in crop protection. So finding antidotes against nerve gases means antidotes against intoxication of people who work in agriculture and use those organophosphates. Now, one could ask why use so toxic family of compounds for crop protection. The answer is simple. They're not quite as hazardous as nerve agents because they are not as volatile, and exposure hazard is not so high. On the other hand, they biodegrade quite efficiently. Just water, rain will degrade them, so that's the reason. Now, these nerve gases has been topic of research for a while, actually, ever since they were first made in Germany, Nazi Germany. And it is, they are all targeting primarily one enzyme that is key enzyme in cholinergic neurotransmission, acetylcholinesterase. So what they do, both nerve gases and organophosphate, they covalently attach. So they form a stable link bond to a protein, this enzyme, and disable normal neurotransmission, normal control of our thoughts, of our movements, and typically acute symptom of intoxication. And the reason why those compounds so toxic is disabling diaphragm that controls how our lungs work. The normal, it's normal function, and people die from suffocation. That's now. So
It's horrible.
yes. Now, why is it not simple to find a good antidote against that kind of compounds? It is that there are quite a few of them, and they are all have slightly different chemical structure. Once they bind with their target, with this enzyme, acetylcholinesterase, they generate slightly structurally different entities. So when we look at structure-based design that is commonly used in design of new drugs in general, then there is typically a target biological macromolecule that is used, the structure of which is used to the antidote, or a biologically active molecule that will, a drug that will control this molecule. In this case, 4 or 5 different nerve agents will generate 5 different targets. And so it is difficult to design a single antidote that will be effective against different warfare agents. Now, so even for classical warfare agents like VX, Tabun, Sarin, Suman, it is still a challenge worldwide to design a really effective small antidote, molecule antidote that will act in minutes and be able to recover activity of this enzyme that is really critical for our life, maintaining life. Now, when we come to Novichok, this new class of nerve agents, actually they have been included in the list, or so OPCW decided, recommended their inclusion in the list of the warfare agents. So they are particularly hazardous because of specific properties that captures, and we can talk more about that. But so that there's another level of challenge that is now created by inclusion of this new class of agents.
A quick question: how fast do the most lethal nerve gas agents work? How long would someone have to administer an antidote if there was one?
Yeah, well, that's a good question. As I mentioned, they're even though more liquids, and so now I'm talking about classical nerve agents. Their vapor pressure differs, and because some of them have a really high vapor pressure, like sarin, they actually evaporate so efficiently that they are poisonous as a gas. That's why they're called nerve gases. Sarin, Soman, to some extent Tabun, but VX is, for example, more of an aerosol. When it is weaponized, it is not a gas, it is aerosol. So gases will act quickly, and exposure scenarios are quite different for those different nerve agents. Sarin, and that's what we have seen in case of Tokyo subway poisoning, where in enclosed spaces like subway cars and the whole system, where gas has stay for a little longer time, then exposure is more efficient. So there was a number of people that were poisoned there because it was a gas. Then that compound gets into people through lungs, and either exposure through aerial pathways, or in case of VX, where it is largely where people are largely skin, some through lungs also, because it is aerosol that is formed. Then the poison ends up in blood. And from blood, it is distributed to tissues, to brain, to fragment. And because all those compounds are neutral, they don't have a charge, they distribute through biological membranes very quickly, in minutes. And depending on level of, depending on where exposed person is located, if person is located at the really ground zero, at the place where gas or this agent was released, exposure will be very quick, and it will be very difficult to save that person, because once we find the exposed person, we have to act in minutes also, and it is within several minutes that it is critical to inject antidote that have been exposed most severely. Frequently, there is no way to save them. However, it is always a whole range of victims that are exposed at different levels. As one moves from ground zero to wider radius, there will be victims that received lower doses, and then they will be easier to treat. So the really how fast one gets with antidote to those exposed is critical, but it's minutes.
Well, what would an antidote look like? Are all the I mean, you're looking just at antidotes, or is there any preventative thing that you could breathe, for instance, that would that would protect you against being exposed to it?
Yeah, there are different approaches in treatment of those exposed to this kind of poisons. Definitely, antidotes are the only real. That's the only real help in those, because we are talking about small molecules that are chemically reactive and that will find this inhibited enzyme and break bond between nerve agent and enzyme, and allow enzyme to reinstate its normal function. Now, the other approach, so this is a limitation of antidotes, that one has to act quickly, inject, if possible, intramuscularly, or even better, intravenous. Very difficult in the field scenario. And then that antidote has to reach inhibited enzyme and recover at least fraction of its activity in order to maintain normal or at least some fraction of normal cholinergic activity to save a person. You mentioned pretreatment. Yes, there is a way to pre-treat. Now we are talking about a scenario where either we are trying to save those people who have not been exposed, but there is imminent danger of exposure. Then they could be given also intravenously, intramuscularly. Also, there are some experiments that show efficacy of that. Larger protein molecules that will bind nerve agent in blood as a sponge. Now, there are different, so basically one has to inject that into potentially people who could be potentially exposed, so that there is additional molecule circulating in their blood that will capture this nerve agent. And also there are some approaches where this molecule is biologically active and will degrade the nerve agent. So those are all approaches that are under investigation and current active research. However, disadvantage of any kind of pretreatment strategy is that one has to expect that exposure will be coming. This cannot, because less effective for saving people who have been exposed already, even though they could be effective even there. And that's in cases where individuals are exposed to large doses. Then large doses of poisons like this can remain from blood. They diffuse into fat tissue, into tissue where there is no target. They will not inhibit anything, but they will stay there and then slowly diffuse back into blood and present a danger over a longer time. So in that case, yes, one could reduce this secondary toxicity coming from nerve agents that was hiding in those depots within our organism, and neutralize that one. But in order to save person and reinstate actual activity of this enzyme that is target, we need antidote, which is chemically reactive. Those are antidotes that we called, most of them are group, family of compounds.
Is there a trade-off between the toxicity of, a nerve agent and how high a dose you can get? Because let's say a nerve agent is really, really, really toxic. That would mean to me that you'd only be exposed to a small amount before you would, stop breathing and being able to breathe in more of it, which would therefore limit the exposure. Is there anything, any trade-off like that? Like this?
Yeah, well, this is an interesting question because now we have different nerve agents that have nominally different toxicity. For example, but they're not all of them are equally hazardous. So let me give you an example. Sarin is not the most toxic nerve agent. It is VX, but VX is not as volatile, and so unless and so a person can move around in area contaminated with VX and not get exposed, while area contaminated with sarin will almost certainly expose individual because it is vapors that a person will breathe in. So even though some of them are not as poisonous because of ease of exposure, they are more hazardous. That's why sarin was used probably more than any other nerve agent so far has been used because of ease of exposure of a larger number of people. Now, Novichoks now come as a third class of compounds, nerve agents in that context, because they are least volatile and they are stable. They can be produced and are stable as solids, and that opens entirely a different way of their use, strategy of their use. That's why they are more suitable in terrorist attacks where they're not released instantaneously, but where individuals, not mass, they're not directed to mass exposure. They're more directed towards individual exposure because one can leave a little bit of powder on a doorknob, on things that targeted individual will most likely touch, handle, and then get exposed.
Huh. When people are people in any condition to even administer an antidote to themselves when they're affected, or are they so incapacitated so quickly that they couldn't even help themselves if they wanted to?
Most likely, those individuals who happen to find themselves at ground zero, where exposure levels are significant, and that's most likely with sarin, or some kind of volatile nerve agent. They will be most likely incapacitated and won't be able to help themselves. The civilian population has no way of helping themselves anyway, because there is nothing if that we carry around where we would be able to help ourselves. Soldiers, on the other hand, have kits, and then they can inject themselves with antidotes, auto-injectors. But even soldiers that have been exposed directly and received high levels probably will not be able. So those that are able to function to the extent to use auto-injector, they will be able to help. So a civilian population will rely on somebody else to come and rescue them.
Okay. So what's your best bet? I mean, if there's so many different types of toxins and they act differently, I mean, how do you form a defense to this? If it's so easy to hurt someone with these things and sicken them, I mean, how could anyone defend themselves? How do you make an antidote that could counteract so many different kinds of toxins?
Yes, well, that's really a challenging undertaking. We start at molecular level. So, the question that you asked is about really a challenging project. What we do is in trying to design something that will be efficient, and of course, in situation like that, in case of exposure of a large population, we don't know what agent is used. So that makes it really important that whatever we use will have some efficacy, will work with several, at least, different agents. So we start at molecular level. We have a structure of our target molecule. We have a structure of nerve agents. We know how their conjugates look like. Conjugates meaning once they incapacitate this enzyme, we know what it looks like. And then based on that structure, we try to find small molecule that will fit area in the targeted enzyme, disabled enzyme, and where the antidote will be able to insert its reactive warhead, let's call it that way, the part of molecule that will then break critical bond and recover activity of inhibited enzymes. So when we find at that molecular level that one particular small molecule is able to cover that activity from several different conjugates, several enzymes that have been incapacitated by several different nerve agents, then we move on to next level, and that is ex vivo studies, so studies where we include not only pure molecules of our enzyme, but also environment where this enzyme is located, and eventually go to in vivo studies in mice where we try to rescue mice that have been exposed with nerve agents, with our antidotes, and those are all different levels of research, where at the end we come up with a small molecule experimental antidote that has good or not so good. So there's whole spectrum of efficacies against different nerve agents. Of course, in order to be able to do that, one has to have access to either actual nerve agents in order to form conjugates with enzyme or expose animals, or use analogs that are not hazardous but can create structure of conjugates, intoxicated enzyme that is identical to conjugates, chemically identical to inhibitor enzymes. So that's typically the way we study those. And I can say that we have we are actually in the middle of studying one particular class of antidotes that, unlike any other, is to adopt the structure of small molecule, of that small molecule, to a structure, not only steric structure, but also electronic distribution of the targeted enzyme, and has, we hope, it will have a better ability to adapt itself to a target, to this poisonous enzyme, and be more effective in treating wider range of different intoxications, soma, sarin, BX, taboo.
Should you have any, is there any way to quickly analyze various gases or aerosols using like an analysis module that would be strapped, let's say, to the wrist or the chest of a soldier, where it could look and see, okay, out of thousands of compounds, we identified this one, and then the person could choose, okay, take this antidote. Would that be a way to prevent people?
Yes, the armies around the world have been using different ways to identify actual nature of the threat. And there was different kinds of detectors that would either change color, somehow indicate what is the likely offending agent. More developed, technologically developed sensors use more sophisticated technology, and yes, that's a really good way to narrow down a threat. The diversity of chemical diversity of these poisonous molecules. However, I'm not aware really of a sufficiently efficient detection system that could be decisively helpful in narrowing down to only one, fast enough so that first responders can rely on that detection. Yes, there are different detection systems, and yes, all those systems are helpful. They rely on chromatographic technology mainly now, but in most of this, detection takes more time than it's necessary than we have in order to react and save individuals. So first responders that come typically at this time of development of all this technology, they have to rely on antidotes that they have. They can't really make this decision, at least in treating people who have been instantaneously exposed now for something that could be coming in hours. Then one could use detection system to identify actual threat.
Oh, so there's no way that you know of to do a fast detection or fast enough within a minute or two?
I don't believe that such system with, as I mentioned, that could be used to decide with sufficient for first responder to be confident that it will be only one. So that's why still it is important to have antidotes of broader specificity, not just targeting one offending agent, but several of them. But that's where we come with developing antidotes in small molecules. And that's where we are finding that any investigation of structural properties of this inhibited biological molecule, this enzyme, is very useful, and technology that Nanome is developing. So this virtual reality is really helpful in terms of providing instantaneous immersive information about the way this disabled protein molecule, this enzyme, looks, and what small molecules of experiment would look like in order to be able to react and rescue this enzyme. So in terms of developing antidotes, that technology is really important.
Yeah. Quick question about Nanome. So it helps you visualize these molecules in 3D, but why is that helpful? How does that help you to to figure out? I mean, can you not test chemically for certain things, but by visualizing the molecules, that helps you?
Yes. The value, this now boils down to question of value of macromolecular visualization. So imagine image of biological molecule printed in a piece of paper in two-dimensional format. That could be analogous to looking at sculpture, artistic sculpture, a photograph of artistic sculpture. Now, if you really want to enjoy art, sculpture, you have to be able to walk around it and look at it from all sides in order to understand what the artist wanted to create in that case. That's similar with a molecule. In order to understand macromolecule, large molecule, one has to view it from all sides, not just from front or back. And technology that allows that is virtual reality. There are stereoscopic visualization technique that allows one to walk around, to zoom in, to go into molecule, where one can not only see cavities and indentations in places where small molecules can interact, but also distribution of charge and potential for combined interaction. So it is observer is now, the researcher is now allowed to use the naturally developed senses to investigate something that is microscopic normally.
And how many molecules can be visualized, and can they interact in the VR environments? What's the limitations of it?
That is a good question. There's probably some limitation. However, I can tell you that the molecules of the biological molecules that I study, and those are molecules that contain about, let's say, up to 10,000 atoms. So imagine having 10 of those molecules, 10 times 10,000 atoms. and I can move them around independently all at the same time. So that is quite a large number of points in three-dimensional space that hardware has to be able to keep track on, and very quickly, because otherwise technology will cause some noise. So whenever whenever individual moves head or changes position, walks around, then everything has to be updated. Of course, that is limited also by hardware, but fortunately, to some extent, graphics cards and hardware manufacturers trying to create as better and better platforms for gaming industry. That's what's interestingly providing motivation for development of hardware. That's also extremely helpful for science, because creating hardware that can display smooth surfaces, a large number of polygons, use large number of polygons to create objects static. Then that also increases efficiency in displaying molecules and number of atoms that we can see, and displaying biological surfaces of those molecules. So currently, hardware, graphics cards, and CPUs that are fairly inexpensive and used, one could say, almost in every home, are capable of running software that Nanowork creates, and one can visualize molecules and manipulate them, multiple molecules, and create actually new molecules, and calculate interaction between small molecules and large molecules, and do quite a few things in virtual reality.
And the way the molecules bend and move and interact, that's pre-programmed in, so they emulate what actually is possible in reality?
Yes, so that is a really critical issue when we talk about science. When we talk about hardware and gaming, all that is artificial, right? So content is created as artistic rendering. In science, we really need experimental data to analyze, and content that is visualized by Nanom software for scientific purposes is experimental data. So all those 10,000 atoms that I mentioned before have been determined experimentally, their exact relative position in three-dimensional space. So when a file containing one of those large molecules, then position of all atoms is something that was previously determined experimentally, and that's where reality comes. And also, different techniques will allow time resolution of molecular structure. So, for example, nuclear magnetic resonance is sometimes used to do that. So one can the scientists who resolve that kind of structures will resolve ensemble of structures, 20 structures, 30 structures of particular molecule, and then using Nanom, we can display them either simultaneously or in as a motion. We can create motion and subsequently display one set, another set, another set, so that we actually can create movie of motion of molecule. And that's also really important. And it happens that this molecule that I'm studying, we have quite a few issues with trying to understand its flexibility and ability of this molecule to adopt shape that will allow different ligands, including nerve agents as poisons, to bind to their active center. The active center is place that is defining biological activity of molecule, in this case enzyme, and it happens in this case that it is located right in the center of about 20 angstrom radius spherical molecule. So there is a narrow channel that leads to that center, and exactly flexibility of molecule, movements of atoms that are fueled only by thermal energy of solution. So there's nothing chemical here that needs to be consumed in order to provide energy for the movement. It's simply oscillations in structure that become critical for properties of those molecules, and we can see that in VR. We can see that.
Okay. All right, very good. So, what last question or so? What do you think is the near-term future for counteracting these nerve agents? Is it hopeful, or is it just a real difficult arms race? What's your impression?
I didn't get the last connection. Is not really good.
What do you think will be possible? Yeah, over the next few years. I mean, do you feel like the nerve agents versus the antidotes is a very difficult arms race? Or are scientists winning, yes, or is it going to get worse and worse?
No, I think scientists are winning in general. However, not so often we come to a situation that we are experiencing now, actually, where something new comes, a new kind of offending agent, new kind of nerve agent, and that's these novichoks come into play. Now, this is where scientists still have to win. So the battle is really uphill battle right now, but I'm confident that we will win. And one of reasons for this difficult situation is that we are not. And now, when I say we, then I mean academic researchers around the world are not really confident about what those novichoks are. That's a little bit of mysterious issue, even though with time, and actually the situation now is much better than 12 months ago. It hasn't been confirmed officially yet. What is the structure of novichoks that was used in England, in UK last year? So we don't have official release to a public or to a scientific that would say this and this chemical compound has been used. We can conclude, and that was part of my research with VR also, that able using VR, virtual reality, to narrow down possible candidates for these offending agents and actually conclude on most likely ones. And so we really need to know what they are by chemical structure in order to be able to counteract them. And because that class of compounds is so hazardous that it is not realistic to expect that anyone outside of specialized government laboratories will be able to have access to them to study them. So for now, we really would benefit from having information and from being able to use in silico approach, computational and visualization techniques to study those structures so that we can create, based on those properties, structural properties, potential antidotes.
Okay, well, very good. Well, Dr. Reddish, thank you for coming on the podcast. And it's scary, but I'm glad people like you are working on ways to to fight back against this stuff. So thank you.
Thank you very much.
You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and share it with friends. Thank you.